Great. So, hi students. This is the Electrical Engineering Pathway Seminar, and today is the Quantum Pathway, and we have Professor Christian Arends, who is the lead of this area for the school, and we're going to let him take it away. So, if you have questions for Dr. Arends, please feel free to let him know. Either you can unmute yourself and ask if he said that's okay, or you can add them to the chat. If they're advising related questions or kind of how this fits into your curriculum, it might be best to do those in chat so one of the advisors can answer for you. But we'll let you take it away. Thanks very much for being here, Professor Arends.
Well, thanks for the introduction. Let me start sharing my screen. I hope you can all see now the presentation I have. Let me rearrange stuff here.
Yeah, there it is.
Wonderful. Let's see. How do I get rid? Excellent. Well, first of all, it's a pleasure to present the Quantum Engineering Pathway program, given that it is such a new field and such a new area. And let me tell you a bit first how I got into the field. So first of all, I'm an assistant professor here in electrical engineering, and my research is focused or centered around quantum control theory and quantum information in a broad sense. So if you're interested, either shoot me an email or visit my website, my lab website, where you find details about my research. And I'm by training actually a theoretical physicist, went into applied math. And I realized in the end, when I got into quantum or quantum mechanics, that the strange world we see there at the small scale, where the rules of classical physics do not apply, I found that very fascinating because you can use these seemingly strange behaviors, which you see here, for example, is an atom, right? Well, the description of an atom where the world is in the middle. So the effects that happen at that scale can be used for modern technologies to invent something new. And that got me that kind of struck me, because in the end, these effects are really, really weird and really, really strange, but at the same time, they give rise to technologies that I feel like can change the world. And so today I want to give you a brief overview what I mean by that, and then what the Quantum Pathway program is basically centered around. So let me jump right into it, and let me start actually with the news. The New York Times, as you can see here. So in 2019, there was an article by the New York Times that commented on an experiment Google has done, and I want to just highlight a couple of things here. Take a look. So Google has performed an experiment with their quantum devices, which we actually can call today quantum computers if you want, where they could carry out a calculation that took 3 minutes and 20 seconds, as opposed to the best known classical supercomputers that could do the same calculation in 10,000 years. So you would agree with me that the best known classical computers, supercomputers, or whatever you call them, are incapable of solving that problem. And the New York Times picked up on that in 2019 because it was such a landmark result. I should say, since then, IBM and other companies started disputing these results, and now the numbers are down to 3 minutes and 20 seconds versus like just a day. Nevertheless, the difference in order of magnitude, again here 3 minutes and 20 seconds versus 10,000, is substantial. So what is this all about, right? Why do we have quantum computers, or why do we want quantum computers? It's kind of obvious, right, if you see that, because again, if you have some problem, some computational task, which it takes 10,000 years with the best known classical computer, well, if you can do that in 3 minutes and 20 seconds, you can see the opportunities that arise from that. I shall say already, we're not quite there yet. So this problem Google's machine solved was completely useless for any practical purposes. Nevertheless, it was the first demonstration where a quantum machine was better, significantly better, than a classical computer. There's another article by the Washington Post that said, okay, FATS put cybersecurity for quantum computing in the spotlight, and that was 2022, because the laws of quantum mechanics, the laws that rule the small world, can also be used for encryption purposes. Namely, you can send a message from A to B that is entirely secure for listening to it. And you can see that the federal government got interested in that, because obviously if you can securely send a message, that is extremely, extremely useful. At the same time, though, quantum computers, so more like this, can also crack our current encryption protocols very efficiently. That's why the FATS get also a little bit nervous about that. So ultimately, again, there was another article by Forbes where quantum computing surpassed, basically was related to this, a classical computer, but that led to, I think that was in 2019, to sign the Quantum Initiative Act into law. That is one of the biggest research endeavors funded by the government in the United States to push quantum technologies. And what do I mean by that? Well, first of all, I should say we have quantum technologies already, right? So MRI machines, lasers, they all are based on principles that we use in quantum physics. But what I mean here is actually new technologies, such as computing, networking, and sensing. So there's this big promise that these new technologies can change our daily life and particularly the world. And let me go a bit more into that. So what I touched on is already quantum computing. What you see here is actually a chip from Google that is in this mess here. You see how control wires going in and out. And this thing where the chip is in the middle sits actually in a fridge that is cooled down to 4 Kelvin. So almost 0 temperature. Why do we need that? Because only at that small temperatures, the quantum effects we want to use to speed up a quantum computation are present. The main enemy of any quantum technology is basically heat and temperature or noise in general. So if it gets hotter, noise washes out what we want to use to see an advantage. And that was exactly the chip called Google's Sycamore chip that was used in this experiment the New York Times reported on. So my background is bit quantum computing and quantum simulation, which is very similar. Simulation just refers to use a quantum computer to simulate the dynamics of a complex system. That could be a chemical system, a molecule system. It could be even larger. It could be a classical system that you have in classical computing, for example, or classical engineering. A typical task a quantum computer is expected to solve faster, for example, could be optimizing a classical circuit. You know, if you ever done digital design already in 120, you probably learned about function minimization and how to write down the shortest circuit to carry out a certain task, which is really, really challenging. Remember Carnot maps, all that kind of stuff. A quantum computer is expected to can do that minimization much, much faster. And not proven yet, though. Anyway, so another big field is quantum networks or quantum communication. So you could think of these nodes around the world. Each node could be a quantum computer. This is actually a quantum circuit diagram that carries out a quantum computation in the end. And in the end, you want to make these nodes talk to each other, right? And you can show that if these nodes talk to each other based on rules of quantum mechanics, that if you want to infer, for example, if you talk from here to here and you want to infer the message that is sent from here to here, the person that receives that message would immediately know if there was an eavesdropper in between. So quantum networks that are based on the laws of quantum mechanics are inherently secure against eavesdroppers. Also, quantum sensing is a very interesting area where you use quantum effects to sense certain aspects, certain things more precisely. What you see here is a surface made out of little spins or electrons, if you want. And if you put a little tip close to that surface, and this is a quantum mechanical object, which we call a spin, this little spin can sense the surface or can get an image of that surface much, much more precisely than if you would just use a classical probe. So all of these new rising technologies basically combine tools from physics, mathematics, computer science, and engineering. So when I started out in the field, when I was an undergraduate student as a physicist, I remember when going to conferences and people were talking already about these technologies, but they were really like proof of principle demonstrations. We're talking 15 years ago, maybe. So the experiments basically filled the size of a room. And I was sitting as a young student thinking, wait, what? What are you talking about? How do you want to make a computer out of that, right? And now 15 years later, we see companies like Google and other companies who are building these things. And the exciting thing for me is that physics is not enough anymore. It has transitioned out of physics. You need mathematics, you need tools from engineering. So that's why I'm really excited to be here in the engineering department, running the pathway program, because you as engineers can bring something very, very unique into the field. You notice that, well, these machines are complex systems. And in the end, we need controls to control the dynamics of these systems. So control theory plays a huge role. In the end, we want to carry out a computation, so aspects from computer science, particularly complexity theory, like that is really important in this field. So the goal really of this pathway program is to this multidisciplinary field to train the next generation of scientists in these aspects. So again, I want to emphasize that it is not physics anymore. It is not math. It is a combination of all of these aspects. And that makes it really, really exciting because everyone comes from a certain background, right? But you can bring in your own expertise to push the field forward and address the key challenges to make these technologies work. So based on basically this principle, this paradigm that it is multidisciplinary, the pathway program is basically organized. Let me start by saying what the pathway class is. So for those of you who don't know what a pathway program is, let me remind you that it starts typically with a pathway class, which is an EE 394 class, and which I'm teaching right now. And I called that class Quantum Mechanics for Quantum Information Science. So this class sets the stage. So basically what I'm teaching is the language and the tools to understand what all this is about. In the end, the language is math, and particularly quantum physics. So if you take a normal quantum physics class in physics, there's a lot of stuff that you basically don't need for going into quantum information science. That's why I redesigned basically a classical quantum mechanics class and tailored it to the needs for quantum computing or quantum information in general. So here again, let me just say, this is really the class that sets the stage. Think of it as digital design, where you basically learn about binary, right, and Boolean algebra and that kind of stuff. And then later on, you learn how do you actually build these things. In a similar setting, you can see this class. You learn the language. You then can go on in electives. So the first one, which I typically teach in the spring, is Introduction to Quantum Computing and Quantum Information. That's where I really outline or describe the fundamental principles of quantum computers. Why are quantum computers expected to be faster for certain tasks? Making that precise. This class builds on this. It is not yet a prerequisite, but ultimately you want to first take this class where you learn the language, and then you go on in this class to apply it. These both classes are still quite theoretical. However, there's another class taught by Professor Gorel, which is a traditional quantum engineering or quantum mechanics class for engineers. It's 434, 591, and he's in the process of redesigning it, focusing a bit more on the quantum technologies that I outlined, particularly how do you build these things. So the focus is shifting in this class a little bit more from semiconductors to more quantum technologies. Ultimately, in the future, we would like to offer more classes, particularly quantum control, quantum optics, open quantum systems, and quantum device modeling. So I hope to offer another class, which I did not put on here in fall 2025, which I call quantum information theory. It's still not yet clear who's going to teach that, if it exists at all. But look for classes in the future that fill the needs. The idea is really that you can branch out into aspects that interest you. Okay, so what do you do then with this, right? I was saying, well, quantum technologies are on the rise. We're not quite there yet. There are, in my opinion, fundamental challenges that we need to overcome. So what do you do if you go through this pathway program, right? What are the job opportunities here? So in principle, when I started as an undergraduate, there was not a single company pursuing any of this. Since then, that has changed quite a bit. So I just list here a few of the companies and startups that pursue quantum technology, particularly quantum computing. So the big players are IBM, Google. I personally work with people at IBM and Google. But Amazon got into the game. There's a big company called IonQ that is in Maryland. Banks, as you can see, HSBC and Chase, they also have some programs. And you may wonder, what are you doing in these banks? Well, in the end, banks are interested in that because they want to know if they can invest into this technology. So if you're not entirely sure if you want to do research in these areas and work for these companies and startups, well, in the end, banks need advisors and people that tell them, well, this is all BS, or is there something to it, right? And if you have a background in quantum computing or quantum information science, and you can tell them, well, there's a lot of hype, but there's a bit of meat, and that is a bit overhyped. So it is important to understand that difference, and people are looking very much forward to that because, again, it's such an exciting field, but surrounded with the hype. And what I plot here, by the way, is the number of startups as a function of time in terms of years that do quantum. So it started here in 1990 with 2. I actually don't know what these 2 are. When I was a student, I never heard about that. But you can see it slowly started increasing up to 2015, 2018. We see this exponential rise. And guess what happened here at 2019 when it went down? well, the pandemic hit, so the whole startup field went down again. But I couldn't find new data, but it's far up again. I would argue that around the world there are more than hundreds of startups. So they're not just companies and startups who pursue quantum technologies. They're also national labs due to national security reasons. The most famous one is Sandia National Labs at Los Alamos. So Sandia is in Albuquerque and in California. Los Alamos, you probably seen the movie Oppenheimer. So I recently actually visited Los Alamos. It was very fascinating. They have a huge quantum computing program in the mountains of New Mexico. The Berkeley Lab and Lawrence Livermore, they're much more. I just list a few here. But then I also want to say that, well, in academia, we need people who train the next generation of scientists and quantum information researchers. That ranges from professors to lecturers to lab assistants and postdocs. Overall, I want to emphasize there is a quantum club at Arizona State University right now, run by students. So if you have not, or if you did not come across that yet, please take a look at these websites. The Quantum Club is just an organization where people get together, we organize seminars together, and so on. And that being said, I want to announce the first seminar actually, where I invite speakers and they speak about quantum computing. The next one is actually this Monday at 10 a.m. in biodesign. If you have not received the notification yet, please take a look at the Quantum Club. They might have announced that. With this, I would say I stop here. I'm a little bit short in time, so we have more time for questions. But yeah, I can just say in the end, for me, it's an exciting area. It's an exciting field because, again, it brings people with different backgrounds together to make this dream or try to make this dream alive. With this, I want to thank you for listening, and I'm happy to answer any questions. Any questions?
I have a question.
Yep.
When will the EEE 394 class be available? Because it doesn't seem to be available for the spring semester.
Give me a second. You mean the
394, the first one, the quantum mechanics for quantum information.
Oh no. It should be taught every semester. So I'm teaching it now, right now, literally, right? I mean, in like 3 hours. And there is another one in spring, so it's offered every semester. I'm surprised that you couldn't find it.
Yeah, it's not coming up in class search when I search for it.
Really? That is really surprising.
Professor Arends, I would just like to ask, do we expect this class to be available on the online campus in the near future?
Let's put it this way: in the far future, yes, for sure. In the near future, I'm not 100% sure. I would say no, because I first would like to establish the in-person program here on the Tempe campus. So ultimately, yes, I hope to have an online version ready, but that will take time. Further questions? Yeah, please let me know. Please shoot me an email if for whatever reason you cannot find this class, because sometimes that happens because they're not listed correctly or something like that. Perhaps Cheryl, you can help with that.
Yes, I can. It says a 498, and I can see it. Intro to Quantum Computing and Engineering, Intro to Quantum Information and Computing. It's there.
But I think the question was about the 394, right?
The 394, this semester is being taught, I believe, by Professor Shankar.
No, well, this one is taught by me. I 100%, right? Because I go there soon.
Okay. Maybe I should talk later.
Probably. No, please let me know if you have any issues finding this class, because obviously you first want to take the 394 where it sets the stage.
Mm-hmm.
However, if you have background, say, in quantum mechanics already, you're welcome to reach out to me to see if you can directly go into the 498. But I would highly recommend doing first the 394. More questions? I want to also emphasize, so if you're interested and you're still a little bit puzzled at what any of this is about, feel free to reach out to me at any time, right? I'm happy to meet and chat and explain you in more detail what this is about and what you can do with it. It is also interesting to note that it links very well to other pathway programs. As I said in the beginning, my background is a bit, well, I should say control engineering, even though I'm not a control engineer. I learned these aspects later on. But if you, for example, take the controls pathway, you can combine these things very nicely with things in the quantum pathway. Because as I said, the tools for control engineering are very much needed to push the field forward.
Professor Ahrens, there's a question in there about the quantum mechanics course 434, which is online, which has 352 as a prerequisite. Those are unrelated. Do you have any comments on the difference between quantum mechanics and what you're doing?
Yeah, so the traditional course, I guess the engineers would take is this one, and typically it's taught by Michael Gorel, I think. The main difference is really the language. So in this class I'm teaching, it's more mathematical, and in the end, math or linear algebra, to be precise, is the language to formulate quantum computing, quantum sensing, and quantum networks in the end. Now, it's again, I always like to compare this to digital design, where you first need to learn about binary, truth tables, and that kind of stuff, right? So my class really focuses more on the mathematical aspects, the language, whereas Michael Gorel's class is more technology-based, basically more application-oriented. If you would ask me, well, can I also take this class instead of this one and go into the quantum computing? I think, yes, you can. However, this class is very much tailored to the needs in quantum computing, whereas this one is not. So that what that means is that the topics that are covered in this class are not necessarily important to understand quantum computing. Moreover, the background you get from learning quantum mechanics this way, I'm not sure if it is enough to go on to quantum computing. So the difference is really the mathematical aspects rather than the technology focus.
Thanks. And do you see this other question from Miguel Langel in the chat here?
My chat is kind of gone. Is it too long to read it?
No, yeah, I'll read it. So he's asking, it's two parts. How much is the noise issue been mitigated or solved? And then he's noting criticism by mathematicians who believe it's not solvable. What are your comments on that? It's a fun one.
That's a fun one, yeah. Because am I on that? So let me answer the first question. The first question is not answered yet. The noise issue is not solved yet. So let's put it this way. Every classic computer has errors, right? How do we mitigate or how do we deal with these errors in classical computing? Well, we add redundancy, right? So if one bit flips randomly from 0 to 1, for example, well, we have still a few other bits that are clean and we simply use them, no problem. That is basically the fundamental or foundation of error correction. Every classic computer has redundancy so that you can do error correction, such that if an error occurs, it doesn't matter. In quantum, that exists too. It's called quantum error correction. But in order to do that, you need to bring the noise levels of the physical devices down to a certain threshold, and that we are close, but only with very, very small systems. And in the end, you want to scale the system, right? 1 bit is obviously not enough to do a useful computation. So long story short, the noise problem is still a problem, a huge problem. And control can play a huge role there because you could think of, well, can we somehow control the processes better such that we can counteract or fight the noise? And the answer is yes, to some extent. And that is partially what my research is about. The second question is there a fundamental hurdle with that? The answer is no. Nobody has proven that there is a fundamental hurdle. However, I would not be surprised if there's a trade-off between how well you can suppress noise through external controls and how much you introduce more noise. That trade-off is a challenge, but it's interesting that you asked that question because the mathematicians, first of all, when you said the mathematicians think, oh, there is a fundamental hurdle, there is no proof or any of this. It's pure speculation. I myself, depending on the day, depending on how I wake up, somewhat more skeptical and feel like sometimes there is some fundamental thing that we cannot overcome. But to the best of my knowledge, nobody has found that yet. So everyone still believes, well, we just need to be better in controlling these things to bring the noise levels down. So first question, yes, key challenge is noise. Second, I don't think it's a fundamental issue. However, I would not be surprised if there is one that comes up in 5 to 10 years or something.
Yeah, a comment from me is you're approaching this based on your background, which is many of these seminars are put out by engineering faculty, but you come from a more scientific physics background, right? And you're asking questions that are not solvable, whereas a lot of our faculty are working on things that have a lot of, I guess, solved problems behind them. Is that fair?
Yeah, well, most people would argue, and I wouldn't disagree with that, but so most people would argue that it is now an engineering problem. We just have to make these devices better, engineer them better. That's most engineers most physicists would even argue that. I'm a little bit more, yeah, there is some truth to that, but I would not be surprised if there is some fundamental thing we first need to overcome. But again, there is nothing in the theory or in the math that tells us, well, there is this fundamental challenge. There are challenges to noise and quantum, particularly decoherence for the experts. That are issues and challenges because noise is not equal noise. Let's put it this way. There are some aspects in quantum that do not have a classical counterpart that are really challenging to mitigate. But again, there are also tools and techniques that can do that to some extent. So
Thanks. And there's another question here, if you don't see it. It says, Elazar is asking, does quantum optics involve lasers?
Absolutely. So what is quantum optics? Quantum optics is the interaction of light and matter. And often we then treat matter quantum mechanically and light sometimes too. But a laser is basically the description of light. Well, to describe a laser, we need to describe it quantum mechanically. Yes. So quantum optics involves to some extent the description of a laser. Yeah.
Thanks for those great questions. Anybody else have questions for Professor Arens or anybody on today? We had some good ones there. Thanks for putting Professor Arens on the spot. We like that.
Again, and I want to emphasize again, I find it really amazing because the program exists for almost a year now at issue. But the students who went through, basically the first cohort who went through these classes, started organizing, right, the Quantum Club. So I would invite you to take a look there, because I feel like it's always it's one thing when I tell you as a professor, well, this is this and this and blah, blah, blah. It's a different thing if you hear that from students, right, who went through it. So I would invite you to maybe reach out to them and ask how it is, what they learned, what the challenges are, and what the opportunities are, to get a better idea. That's why I cannot emphasize enough the Quantum Club at ASU.
Yeah, that club might have, there's a final question here from Samuel asking about a reading you would recommend to get a better understanding of the subject and the technologies. I imagine that the club might have some recommendations, but do you have a fundamental reading that they could do?
For sure. So it's a bit challenging because the main hurdle in quantum is the math, right? Everyone always like, oh, quantum mechanics, it sounds so complicated. And in the end, it sounds scary to some extent, but it is not. And the challenge is that you either have books that are really, really mathematical, you open the first page and you think, oh my God, what the heck is this? Or you have books that just don't go beyond, like I call it the Sedona quantum mechanics, where it becomes a bit esoterical. However, there's one good book. Let me just pull that out. To get an idea of what quantum computing is about, it's called Q for Quantum Computing by Terry Rudolph, that tries to develop the principles just based on a formalism that doesn't require any math. So the book I have in mind is Q is for Quantum by Terry Rudolph, a very famous professor who founded a company, now a quantum company in the Bay Area, PsiQuantum. The other book I would highly recommend, that is more like from a computer science perspective, I would argue, is by Scott Aronson. And the book is called Quantum Computing Since Democritus. He has a really interesting style of reading it. And in fact, that's how I got into the field. When I read, it's kind of funny, but when I was a PhD student, my advisor recommended that book as like a book to use at nighttime before you go to bed. And I opened the first page and I started thinking the whole night about this whole subject because it is so intriguing. So both books are really, really good. Again, Cues for Quantum by Terry Rudolph and Quantum Computing Since Democritus by Scott Aronson. That is, I think, a good read to get an idea what it is about.
Great. I'm putting both of those in the chat so they can see it. And then there's we'll take this final question. An online student is curious. Besides, we did talk briefly about 434, which is available as an online course. That's really the only other course at the moment that we have that touches on quantum mechanics. But I imagine that the students curious about quantum can follow the links to the club and learn a little bit more, and definitely get into these books. Any other recommendations for those folks? Because remember, these pathways are very introductory, so there's nothing really stopping you from getting a base level knowledge. But any other comments until we get this thing online?
Yeah, one thing I would like to emphasize. So IBM, the company, has now a big quantum program, and they have online tools. It's called IBM Qiskit, Qiskit, where you can actually access via the cloud their quantum computers and play around with it. It's Python based, and you can play around with these devices. You can learn. They have a really, really good online tool to learn the fundamentals of it. Take a look there because that gives you a pretty good idea of what it is about. I think, no, I'm not saying this yet anyway. No, sorry.
Well, thanks. I think that hit them all, and we're about at time. So students, I put all this stuff that he mentioned in the chat here, I believe, and including that last link to the IBM Qiskit. So we're at time. So thanks very much for your time, Professor Ahrens, and thanks students for your awesome questions. And we really appreciate you all being here.
Sure. Thank you. Bye-bye.
Thanks all.